Good afternoon. Welcome to the final industry forum session. I hope you're all having a good time at the VLSI Design Conference and, like me, learning a lot. And it's really interesting times because Indian government also so much interested in the VLSI, silicon, and I never thought I would get a second innings in the semiconductor industry, honestly. So this is one of the best times to be a silicon or a VLSI engineer. And it's my pleasure to welcome all of you to the fourth and the final industry forum. It has been so far so many exciting talks from various industry leaders. So currently, it's my pleasure to introduce Shivraj, who is currently Director of Design Engineering at Global Foundries. He is the India site lead of Technology Enablement Team at Center of Excellence, Bangalore. His team is responsible for developing IP, foundation IP memories, test chips, and RF benchmarking circuits for Global Foundries. He has earlier worked at Motorola and Intel. He is also an adjunct faculty at many prestigious institutions such as BITS Pilani, BITS Hyderabad, NIT Goa, IIT Tirupati, and SGGS. So today, Shivraj is going to talk about silicon photonics, opportunities, and challenges. Shivraj, over to you.
Hello everyone. Today I would like to discuss about the silicon photonics, the opportunities that we have in this domain, and what are the challenges that we need to overcome in future to make this a mainstream technology. So today, silicon photonics refers to a chip which has both photonic devices as well as electronic devices co-packaged together. So we know that silicon photonics has been maturing over the last 2 decades, and its compatibility with the CMOS process lines have helped a lot for its rapid growth. So generally, silicon waveguides are fabricated on SOI wafers. The waveguide is on the silicon device layer, which serves as the core, and silicon dioxide is cladding. Due to the index contrast between the silicon and silicon dioxide, the optical mode is well confined in the core region. This index contrast also helps in fabricating the band, tighter bands, right? These straight waveguides and band waveguides are used in various silicon photonics devices. We make silicon photonic devices out of it. And importantly, we use the 1310 nanometer or 1550 nanometer wavelength because in this region we have a low absorption loss. We have various types of silicon waveguides like ray waveguides or strip waveguides based on the construction. So silicon photonics, as I said, electronics and photonics together on a single package part, right? This was a vision of Sorev, a famous scientist, who was saying that we can, 1995, he claimed and demoed that electronics and photonics can be, put together in one package, one chip, and we can realize the functionality that we want. So today we know that Intel like company has a product which is a transceiver running at 100 gigabits per second, standalone silicon photonics product, right? So basically, what we are saying is this integration, monolithic integration, can help you to reduce the size as well as the cost-wise. Also, we can reduce the cost of sending the data with a very high frequency rate, right? So if you see the trend today, what is happening in data centers, we have advanced data communications and so lab on chips. These are the very well-known domains in silicon photonics today. But in future, there is a lot of uses of silicon photonics in quantum photonics, micro photonics, and LiDAR applications. So what are these applications, right? These chips, especially the transceiver chips, finds applications in data centers, right? I said, which is having the maximum share in the silicon photonics industry. Research is right now ongoing to increase the amount of data rate, right? So different methods of coarse wavelength division multiplexing or dense wavelength division multiplexing is used. Advanced datacom deals with having different ways to use the wavelength division multiplexing. And another area, today industry is using silicon photonics is lab on chip, sensors, where you can imagine we put a blood plasma on this sensor. So based on basically the refractive index change, the top carrying material changes. It's reflected in the effective index of the mode, and so resonant device will have shifted resonance when any analyte like blood plasma is put on the top of the waveguide, and based on that we can detect what kind of disease a person has, right? So there are a lot of application of silicon photonics in quantum domain also. Mostly high pump power is required in quantum and nonlinear domain, where due to high power, two photon absorption comes into the picture, and generation of signal and idler, photons is possible, and these will give rise to generation of photon pairs, right, which find a lot of applications in quantum domain, like QKD, that is quantum key distribution, and so on. So another emerging domain is in the RF microwave photonics, where RF signal is mixed with the optical signal, and signal processing is done in the all optical domain, and then this is fed to the photodiode and then converted back into the electrical signals. And the last one, the LiDAR application, which is very prominent in automotive industries, where phased array antennas can be built with the grating structures and can be used as small chip antennas in the automotive. So this is a file which is talking about the stacked structure. You can say that all the elements required, like for example, grating couplers, germanium photodetectors, waveguides, modulators, and MOSFETs, which is like a electronics, right? Semiconductor, traditional semiconductor, right? All these are done on a single SOI wafer. The main advantage of these materials are they are all CMOS compatible and can be manufactured using the standard CMOS process lines, which reduces the cost and makes it more adaptive. So all the steps like photolithography, etching, diffusion, oxidation, these are all common when we build silicon photonics stack on the SOI wafer. Now, what are the different silicon photonics passive and active devices, right? So silicon waveguide mostly operate around 1 micrometer to 3 micrometer wavelength range, but these silicon photonics devices broadly categorize into the passive and active, and the passive devices are the ones which are mostly made with waveguides based structures, while the active devices are from different mechanisms like electro-optic or thermo-optic waves, right? And top left, you can see there is a 1/2 MWI multi-mode interferometer structure, which is used as a power splitter. You can see that power coming here, and power is split into two domains, right? So bottom left shows the SEM image of the micro ring resonator, and you can imagine this as a capacitor equivalent in electrical domain, right? So this can be used in filters, sensors, switch, or modulators, right? And this is a cross-section view for PIN diode or PIN diode, and basically these are like electro-optic devices, and we also have devices called thermo-optic devices, right? So the heat produced by a thermal heater can really shift the wavelength, and we can really measure the temperature on the die or something. So you can really build a thermal sensor using this idea, right? So how to extend the wavelength is one of the challenge today in silicon photonics. People are working in the research area, where that there are visual near infrared spectrum. We have a near infrared spectrum, mid infrared, and long wavelength infrared spectrum, right? And they have different wavelength range. So generally, as I said, 1 micrometer to 3 micrometer wavelength range is what we use, but we extend it by using the different device engineering, right? We use the silicon silicon dioxide, there's silicon nitride, we have germanium silicon interface, right? All these will help to basically extend the wavelength for applications in the silicon photonics. So silicon nitride with silicon can be used in sensor applications. Germanium with silicon will help in photo detection. Silicon germanium quantum well based modulators are being built, and 3 and 5 group elements are integrated for building the on-chip lasers. Also, you can see this PIN diode. You can see silicon germanium here, and this N plus and P plus doping. So this germanium photodiode also can be built, and these are the IV curves for this PIN diode. So based on how we make the structure, what materials we use, we can realize the different characteristics of those devices and used in various applications. So this is a file which is talking about one of the important application of silicon photonics, that is single channel photonic link, where you have the data in the electrical domain goes to the driver, and then with the thermal control it is modulated. The laser source is coming here, so the data is going to the silicon waveguide, and this is a you can say data in a photonic world or optical world, and then fiber will take it to the you can say electronic world, where photodiode will convert that light into the electrical signal and goes to transimpedance amplifier and again convert into electrical. So this is single channel photonic link, the cartoon structure, right? And we can use the wavelength division multiplexing to increase the bandwidth of the data transmitted from transmitter to receiver, right? And this right side portion shows how the electrical circuits and optical circuits, we can put together, right? In the electrical circuits, we know there will be transmitter, receiver, serializer, deserializer, like modulator, driver, and so on. But in the similar way, on the optical domain, we have grating couplers, modulators, fibers, filters, and photodiodes. And if you want to really find out what is the total energy consumed by this electronics photonics together, a chip, then we need to find out what is the total power consumed in the electrical domain, what is the total power required in the laser side, and then you can calculate the total picojoule per bit that we can spend for realizing this kind of link. Okay, this is another example where this is from Global Foundry. Silicon photonics monolithic electro-optical integration. It is shown each of the elements shown here, either it's CMOS side or optical side, is all silicon proven, and today there are multi you can say hundreds of millions of dollars of basically the revenue coming out of it, right? And we are integrating all the optical as well as CMOS elements together to realize CMOS photonic IC. So opportunities in future, if you see, right, how the evolution of data center applications are happening. Initially, the pluggable optics were there, then this onboard optics, then 2.5D co-packaged optics, the 3D co-packaged optics, and now 3D co-packaged optics with integrated lasers. That is the trend, right? So this is the evolution happening, and these are the opportunities for us to make smaller, low-cost devices which are plug and play in various applications, right? Silicon photonics device improvements are required today. We need high-speed silicon modulators, we need high-speed detectors, optical amplifiers, on-chip lasers. All these need to be working at high efficiency, and also high efficiency fiber to chip couplers are required. And various architecture today are tried, like we do in a electrical domain. PAM4 already serial IOs are available, right? Today, wavelength division multiplexing is a key mechanism used to increase the bandwidth of the signal in the optical domain. Idea is putting the silicon and CMOS electronics together. So the matrix we use is what is the power consumption, what is the energy per bit, and how much bandwidth, optical bandwidth we can achieve. And in the immediate future, we want to work on co-packaged optics, high performance computing, like we have already heard about quantum computer, right? So programmable photonics. This is not FPGA, but this is FPGA, programmable photonic, basically programmable gate array. And the graphic processing unit also, a lot of photonics is being used today. So if you see the innovation opportunities, I think silicon photonics is in everywhere. Data center, automotive LiDAR, lab on chip, right? Optical computing, gyroscope sensors, 5G, 6G transceivers, optical interconnect. You can see that there are so many applications. So what our team is doing is today, GF may have almost like we have $100 million business on photonics, but we see that there is a huge potential and this business may grow up to $10 billion in 2035. So what our team is doing is today demonstrating the technology capabilities to the clients to get the design win. We are influencing the differential technology development. We are also helping the PDK team to validate the PDK and develop the reference design flow, and also generating IP and patents to have a long-term differentiating solution from GF, right? So these are the many players working in silicon photonics area, and most of them are GF customers. So tremendous opportunity for innovation. And with the opportunity, there are challenges. If you see the research areas, right, GPON or optical interconnect, optical computing, automotive vehicle radar, these are various research areas. But one thing cannot fit into all the applications. So we have a challenges that certain application, for example, automotive vehicle radar, you may not be interested in high speed, but you will be interested in low power and low noise, right? We need to see that present solution is compatible with on-chip electronics, should be such that electronics and optical can be put together, and at the end of the day, everything has to be a lower cost. So disruptive products and applications require design innovation and technology co-optimization, and that is the major thrust area in silicon photonics today. So we were seeing, what is the future and where is the pipeline going to be for expert engineers. So we tried to talk to some of the IITs and IISc, and luckily we found that there's a lot of work happening in silicon photonics. So for example, Mr. Vijay Krishnadas in IIT Madras, he's working on silicon photonics device and circuits, RF photonics, quantum photonics, FPGA, lab on chip sensor. So he has 9 PhDs and 2 master students working on silicon photonics area. So similarly, in various IITs and IIScs, we have many PhDs and master students working on silicon photonics. So we have good pipeline of engineers available for future growth, and we feel that India can contribute immensely in the silicon photonics domain, and be part of this growth opportunity available for everybody. With that, I will stop my presentation and open for question and answer. Thank you.
Yeah.
Vijay, you need to unmute.
Thank you, Shivraj, for this wonderful talk on silicon photonics. It was really, really very insightful, and I learned a lot from your talk today. So, Shivraj, I cannot resist from asking you this question. So we are talking about a lot of fabs starting in India and all that, right? In view of this background of what's happening, right? How hard or how easy is it to set up a silicon photonics foundry in India? And what do you think are going to be the biggest challenges? And it's very, very nice to know that already universities are already working on the design side of the things, right?
Excellent question, Vijay. Actually, I was in one of the panel discussion, ISA, and one of the topic I was telling is what India can do is silicon photonics, because we have SCL Chandigarh, Bharat Electronics, we have some IITs, some small setups for doing at least we can make the MOS capacitor, characterize it, and we have some way. So this is not going to need billions of dollars of investment that we need for a new fab or something. Silicon photonics uses the same process technology I mentioned, right? All the steps: oxidation, etching, photolithography, similar steps. We just need to build these active passive devices and then connect it. So I feel that compared to building the latest technology node fab,
Right.
spending $7-8 billion versus this could be like a less than $1 billion, and Indian government today already placed $10 billion. I think this is coming a very big way, because without silicon photonics today, data center, the links, it's very hard. Electrical links are very difficult to design. It takes 1 year to design, 1 year for validation, and then we are not reaching to the speeds that is required today. As I mentioned, Intel has the whole link, silicon photonics link. We have a tremendous opportunity to not just build those links, but there are various applications I mentioned. So to answer your precise question, yes, it is possible. Only thing we need to do is the desire to invest and make those devices, construct them, characterize them, and make them stable. And on top of that, we need the different PDK, because this photonics is, different. So we need to develop those PDK, but it is very much possible. And whoever can see that, $10 billion is, we are saying only GF alone will have that opportunity. You can see worldwide, there will be tremendous opportunity, right? So this is the right time to invest in silicon photonics like technology, where everybody is trying to learn and build those things.
Okay, thanks, Shivraj. That's very, very encouraging to know. So I was in the last panel I was hearing where Naveed had a very good point that if anybody can make this happen, it's going to be the core team of this committee, VLSI Society of India. Definitely, I think we should take this up with them. And sounds like it's a lot cheaper to invest in this technology, and the ROI is really, really great. Thank you, Shivraj. And we do have a question from the audience. I'll just read it out for you. We've heard of glass substrates for photonics. What's the state of this today? This is a question from Venkatesh.
Yeah, I think definitely that is one of the possibility, right? Because today, if you see, right, we already have various substrates, to reduce the cost or to get the different characteristics. So that is also one of the possibility. So yes, we can have that, but we need to do a lot of research, modeling, characterization, and make sure it works. And the reason is what? The cost is a reason, or a better characteristics reason. We have to find out and use it. But I don't think today anybody is building the product with the glass as far as I know.
Okay, thank you, Shivraj, and thanks for your time and for this very insightful talk on silicon photonics. And yeah, we'll connect offline.
Thank you so much. Thank you for the opportunity.
So over to the next talk. So we have another interesting talk from Venkatesh Tika. Venkatesh Tika, just to introduce him quickly, he graduated from RAC Surathkal. He started his career in Texas Instruments by working on mixed signal IPs. Later, he joined Cosmic Circuits and worked on ADCs, DACs, LDOs, band gaps, and analog front ends. After Cosmic was acquired by Cadence, he was the director of Analog IP division, and he worked with several tier 1 companies in taking up their IPs. In 2017, Venkatesh moved to image sensor hardware division at Samsung, and currently he's led to create the world's first higher than 100 MP sensor. So today we are going to have a very interesting talk on challenges in design of high megapixel mobile cameras. Over to you, Venkatesh.
Thank you all for giving me this opportunity to speak in VLSID conference. The topic of the discussion of the presentation is the challenges in designing high megapixel mobile cameras. So to give a brief overview of the presentation, we'll first look at how to compare a camera with a human eye, and what is the market of the mobile image sensor, and the market for high megapixel image cameras, the key challenges that we face in designing these high megapixel cameras and how to overcome them. And then we will summarize the key item I want to present in this presentation. So to begin with, let's say you want to compare a human eye and a camera. At the outset, it may look very similar. The human eye has a retina, which is equivalent to a sensor. Human eye has opening, which is equal to aperture. So we will try to see key comparisons between the two. Okay. First of all, the resolution. The resolution of human eye at the center is very large. The pixels are more in number, but as it goes away from the center, the density of the pixel reduces. Whereas the highest megapixel mobile camera that is available in the market is around 200 megapixel. If you compare that, the human eye's highest density and its full field of view, it will be equivalent to around 576 megapixel, which is huge. Pixel density, as we said, is uniform in a mobile camera because you would use it to display it on a screen. So the density of pixels is expected to be uniform, whereas in a human eye, only foveate, the human eye moves around the area, so it tracks the area of your interest, and the brain constructs the image. In the other angle of comparison, camera can be still or video capture, whereas the human eye is primarily similar to a video camera. It doesn't take one snapshot, but it recreates the moving image. In terms of dynamic range, this is one place where the human eye is far better. It's able to resolve 20 to 24 bits, whereas typical camera is able to get to 10 to 14 bit dynamic range. In terms of frame rate, this is where the cameras do much better. They're able to get to 960 FPS in mobile cameras. There are cameras which have even gotten to 7,200 FPS for a very short duration. Whereas human eye is around 24 to 30 FPS. So the main goal of this talk is to see on the one vector, on the resolution vector, how and what can we do to get to human eyes comparable resolution in the full field of view. Moving on, to give a brief of how much is the market price for this image sensor, roughly around $26.3 billion is the expected market in 2024, growing very rapidly. And the average resolution of a phone, including all cameras, is expected to become 112 megapixel. And the number of units that are expected to be sold is around 5.8 billion. This is including all the laptops, mobile phones, primarily driving these things, as well as any other devices that are using the sensor. One key aspect is, as time is progressing, the cameras are having more megapixel resolution in their cameras, right? So the rear main camera is already having more number of 32 megapixel plus kind of cameras, and the front camera, which is your usually selfie camera, they are also catching up. Okay, so as you can see the trend, more than 56% rear cameras will become more than 32 MP sensors in few years. To dive into the key topic of this discussion, what are the key challenges in making a high megapixel camera? Some of the things that I have noted, there are far more things that are done in the real world. Thermal shading, it's a very interesting aspect specific to image sensors. There is a specific kind of a noise called smear-like horizontal band noise. We will discuss what is it, how to resolve them. While the number of pixels are increasing, how do we still achieve high speed? They seem like something going against each other, but the customer requirement is still to have more megapixel as well as have high resolution. Along with that, we will see some key digital techniques to overcome some of these non-idealities in the image sensor. Thermal shading. So if you were to see on the right side, you have a a typical image sensor, which is a stacked die. The bottom die is a logic die. If you see here, the logic is concentrated at the center and on the top side. A MIPI is sitting at the top. So as the logic density is more, the power density in that location becomes higher. In a stacked sensor, the pixels at the top of these are a little bit more heated, as seen in the left diagram here. Once the pixels are more heated, the dark current in those pixels will also increase. Due to this dark current, if you take an image, it will look like it is having a shade. Here it is having a shade where the logic density and the functioning of the logic is most here. The highest power density seems to be here, which is driven by a MIPI. So these things make the look, the image look little shaded at the dark image settings. And if you reduce the amount of aperture open, the dark current accumulation also reduces, as seen in this graph. So typically the dark shading measurement is done around 125 millisecond. That's the industry standard. So we will see how to tackle some of this. One of the method is, if you see the highest area of power consumption density, the power density is in the MIPI. So one of the method that is used is use the MIPI in ultra low power saving mode. So what that means is, if you're measuring this dark image at 125 millisecond, the MIPI is usually on for 30 millisecond or so, and then you can shut it down. So that reduces the power consumption. Another technique, very tricky technique is as you see in the figure on the left side, if you do a normal sensor, you are seeing from the coldest region to the hottest region, the temperature difference is around 3.1 degrees centigrade. Now, if you were to put intentional heaters at the coldest area, it will heat it up. So it will burn a little bit of power, 30-40 milliwatt of power, but still the temperature difference dropped down by almost 2x, 1.5 C. So it's a neat trick which can help to reduce the amount of shading in a thermal sensor. So the other techniques could be using a better thermal coefficient package, using the logic to be spreaded more evenly in the sensor. And perhaps one could be the MIPI, the SERDES, to be made bigger so that it consumes with a lesser power density, and heating up reduces a bit. So unlike in a processor where 10 degrees C temperature difference in your die is perfectly okay, in a mobile sensor, mobile image sensor, it becomes a very tricky challenge to handle it. One more type of noise. If you have an image which is dark, but there is one place where there is a very bright object. So if you see in the right side, you have a street light and the whole background is black. But if you see in the whole row where the light is bright, the dark area also gets a sort of a bright a shading. Okay, this is called as smear light horizontal band noise. Why does it occur? Typically, the bright pixels hit the common circuitry which is all along the row and makes that band appear. How do we take care of them? We ensure that the power supply is routed well. You ensure that the settling is done correctly. And of late, there are methods wherein you introduce a dummy column to the left and right side and see any error that has come through on them and digitally correct them. So there are various techniques to take care of it. The older phones didn't used to bother too much about it, but of late, most of the flagship phones will have some sort of correction or method to take care of SHB. And it's very annoying if you see this in a mobile camera. Moving on. As I was telling, if you were to do a large megapixel, large sensor with more megapixel camera, the road drivers, if you see an image sensor, the left side, right side is driven by a road driver, and in each column you typically have a ADC. So as the chip size increases because of the need for more megapixels, the circuit becomes slow. Because the chip is bigger, you have to drive a longer distance, and each pixel has to drive a long column to drive the ADC, which is sitting at the bottom. So some of the methods is in summary, it is more like, can we parallelize the processing? So using more columns, you can stack one ADC on another. So you can process more lines. Instead of one, you could process 2 to 4 rows per at a time. As well as you could perhaps drive the circuit from both left side and right side. So that will reduce the peak resistance by around 4x. So by using parallelism and using multiple drivers, one could still achieve high-speed operation even if you have more number of megapixels and a large sensor. Moving on, in many of the sensors may not be specific to high megapixels. There are lots of digital techniques which smoothens the image, which process the image upfront before it is sent to the application processor. So some of the key digital techniques that are there in the sensors are, if the first on the left side is bat pixel correction. You have 200 megapixel, even if you have 1 ppm error, right? That's around 200 pixel, which will be bad. Even in the best controlled process, 10 ppm kind of error will occur. So all these bad pixels, even in 1 pixel is bad in an image, right? It really pops out. So there are techniques in digital to store these bad pixels in a memory and then correct it when the image gets produced. The other aspect is in a lens shading correction, wherein a normal lens will produce the brightest image at the center, and as it drops off to the edges, the image brightness could be as low as 60-70% of the central area. But if you see the image that is displayed on your screen, it's usually uniform. So what we do is a reverse function of the lens is applied, and that is done in digital. Another aspect is the HDR, high dynamic range. So if you see the right side of the image here, the brightest area becomes very bright and the dark area is almost invisible. So with analog and digital together, what we do is we reduce the brightness in the brightest area and increase the brightness in the darkest area. So it becomes more similar to what the human eye can perceive. Another aspect is fast autofocus, wherein the pixel array and the digital have capability to measure the distance and quickly focus the lens. Instead of doing a binary search, it will be able to directly go to the setting it needs. So that is another aspect which is very key in video recording and image sensors. And that is another technique which is a combination of digital and analog technique to achieve in the high megapixel sensor. That concludes the key items I wanted to convey in the presentation. In summary, the mobile image sensors are moving to more megapixels. It enables large zoom in a bright light condition, and in dark condition, you can combine these pixels and get better SNR. Customers still expect high frame rate at HD and FHD mode, along with high pixel count. So these two go against each other. Some of the techniques I shared are used in designing them. There are also various new techniques in digital which are done to ensure the pixel quality, the image quality is good even with high megapixel. So as I see it, the mobile image sensor are moving towards giving a pixel density as good as a human eye in the full field of view. That's with that, I would like to conclude this short presentation. Thank you.
Hey, thank you, Venkatesh. That was very insightful. The first slide almost took me back to my biology class. Um, yeah, I think it's really, really hard to mimic anything human. I know we are doing a lot of machine learning, artificial intelligence, but the number of megapixels that a human eye can process, oh man, I think it is incredible, really, really. So, Venkatesh, I do have probably maybe quite a lame question. I see that multiple cameras are stuck into mobile phones these days. Even the selfie cameras are having 2, 3 cameras, right? So, what are the things? How do you kind of triage all the information coming from multiple cameras per se?
So, see, the primary purpose of the cameras, right, is you don't have a zoom capability in the analog zoom capability in the phones, right? So if you want to see a long distance one type of camera comes into picture. There is another one which comes into picture in wide angle of view. I don't think they try to combine them, but which one to use, they will figure out. I
Oh,
don't
I see.
see
Okay.
like 5 of them being used at the same time to try and get the image. Power will be too high, and even the pixels, right, are so high right now that processing that itself, both the sensor and the application processor, right, are going neck to neck. Qualcomm, I think, released a 200 megapixel processing
Right.
unit about a year back, but the sensors have already reached 200 plus now.
Right.
So that's just the processing of the still image in one camera is going to take the juice out of the sensor of the application processor. So I don't think all 5 are used, but they're used for different applications. Combined together, all 5 can give you almost like a DSLR kind of range of the images. Yeah.
Oh, okay. Okay. Thanks, Venkatesh. And I do know I work on the physical design of this camera macros, and I know that power is a super duper challenge on these. And yeah, and yeah, so lots of ways to go before we catch up with the human, I guess.
Yeah, yeah. Perhaps in a couple of 3-4 years is where we might hit 600 megapixel. Yeah.
Yeah, yeah. Thanks, Venkatesh. I don't think we have any questions from the audience. And yeah, thank you for this very insightful talk at the industry forum.
Thank you.
Over to, yeah, next to Ravi. So it's my pleasure to introduce Ravi Nagaraja. So Ravi used to be my colleague at Qualcomm. So hey, good to see you, Ravi. So Ravi currently is a senior director and site head for ST-ADG India. He heads the automotive SoC and IP development for microcontrollers, infotainment, radar, and ADAS. Prior to ST, he has spent several years with Qualcomm, Intel, Infineon, Agilent, and Oki in the space of SoCs, IP, and design systems. And I can tell you, Ravi is an industry veteran. So Ravi is going to talk about enabling industry trends, smart mobility, power and energy, IoT, and 5G. Over to you, Ravi.
Good afternoon, everyone. My name is Ravi Kudli, and I head the automotive group at ST Microelectronics India. It's my pleasure today to be a part of the VLSI Conference 2022. Today, I'll be talking about some of the key industry trends and enablers for semiconductor demand and innovation. ST is one of the world's largest semiconductor companies. Our 2021 revenues were close to $13 billion US. Worldwide, we have 48,000 employees, out of which 8,400 are in the R&D, over 80 sales and marketing offices, 13 manufacturing sites, and we are also signatory to doing business responsibly. We address 4 end markets: automotive, industrial, personal electronics, and communications, computers, and peripherals. Sustainability is an integral part of ST's value proposition. How do we do this? We create technologies for a sustainable world, we prioritize people, we protect the planet, and we generate long-term values for all our stakeholders. Commitment to carbon neutrality. ST will be carbon neutral by the year 2027. All the milestones are in the process of being met. Collaborative programs and partnerships are in place for carbon neutrality throughout our ecosystem. Semiconductors, they're getting stronger, and the demand for semiconductors is growing phenomenally. The total available market, as you can see, 2020, 2021, and 2022, tremendous growth. 2022, the market will be upward of $600 billion US. So what are these three strategic enablers for electronics and semiconductors? Smart mobility will be an extremely important vector, power and energy, and Internet of Things and 5G. I'll get into the details in the following slides. What do we mean by smart mobility? Of course, making driving safer, greener, and more connected for everyone. We intend to increase the safety for road users, driving comfort, and convenience. We need to make the cars affordable and electric vehicles more desirable. Finally, cleaner, greener internal combustion engines are in need of the day. Just a data point, electric vehicles in 2019 were about 9%. 2025, this will be close to 20%. Internal combustion engines, despite the popularity of electric vehicles, will still continue to be in the range of 90%, at least for the next few years. What are the challenges for automotive transformation? We need to make our cars safer, more friendlier towards the environment, more connected, more convenient, and more affordable. So how do we address these challenges? We address the challenges through car digitalization. What are going to be the key components? Assistant driving, autonomous vehicles, software reconfigurable vehicles, and cloud connectivity for big data harvesting. Net, this will increase the semiconductor content and demand per vehicle significantly. In the meantime, the innovation for car architectures has been progressing at a breakneck speed. Compare a car of yesterday and compare a car of today. There's been a need and demand for 10x increase in the computational power. Much higher performance and real-time capability is needed today. Support for high speed and in-vehicle communication is extremely high. Over-the-air software upgrade capability needs to be very, very high. Redundancy and automotive safety, which is built into the car, is an absolute must. So these are the 4 or 5 areas which are going to be driving the computational power requirement of a car. Two key mega trends are driving the silicon demand, semiconductor demand. ADAS, an extremely important component which will grow by leaps and bounds, and car electrification. As you can see on the left side of my slide, the electrification total available market 2022 was $4.3 billion. 2023, this will be $5.7 billion. ADAS on the other side, 2022, $6.8 billion, and 2023 will be upward of $9 billion US. On the right side of my slide, you can see the average semiconductor content per car. In an internal combustion engine car, it's close to about $400 US. In a hybrid car, it is close to about $700, whereas in a battery electric vehicle, it's going to be upwards of $1,000. So you can look at the ADAS and the powertrain, two key drivers for the next generation cars. And this is going to be propelling the semiconductor demand through the roof. Second vector, which is going to be driving the semiconductor demand and innovation, is in the space of power and energy. There's been a continuous rising demand for usage of electrical energy, decrease in carbon emissions to reduce the global warming impact, and of course, a push for increasing of the renewable energy. Some data points, as you know, there's been a 30% global increase in electricity demand over the last 10 years. And in the case of renewable energy, we will see a 10% increase from now to end of 2030. So a great increase in renewable energy demand. What are the challenges in power systems? Power systems today need to be of greater and higher efficiency, higher performance, better form factor, lower system cost, and faster time to market. How do we address these challenges? Reduce the power losses throughout the system from individual components to overall system. Increase power in the system, which can handle much more efficiently, increase speed of operation. Reduce the system size through higher density components, smaller packaging. Reduce the cost of individual components, increase the amount of integration, reduce material space, and reduce the design cycles, reduce the testing and industrialization cycles, have pre-integrated solutions. Hardware and software need to be a lot more efficient. Silicon carbide is going to be a game changer. It's already a game changer in the need of power systems. Why is that? It's all about the band gap. So silicon carbide allows power devices to go beyond the physical limits of silicon. As you can see on the left part of my slide, silicon carbide conduction band is 3x larger. Silicon is 1/3 of it. So what this means is silicon carbide can deliver smaller sizes, lower energy losses, higher voltages, higher frequencies, and higher temperature tolerances. ST is a key player and a driver of silicon carbide solutions in key applications. The biggest application, of course, and the usage and the utilization is in the space of automotive and industrial semiconductors. So in the case of automotive, traction inverters and onboard chargers and charging stations, these will be the two largest beneficiaries of silicon carbide solutions. Longer driving ranges, faster charging, and reduction in the car weight. On the industrial side, increased power efficiency, reduced total cost of ownership, and smaller, more compact machines. So the benefits are phenomenal. You can see some of the metrics listed out here. For example, in the case of automotives, upward of 600 kilometers driving range with silicon carbide. Silicon carbide charging stations can give 2x the needed energy demand and close to 200 kgs of weight saving on an average electric car. Whereas on the industrial side, 50% lower energy losses and at a 5x frequency. Cost of ownership can be reduced up to 20%, and smaller, more compact machines, which means that size and weight up to 80% with an average reduction of 50%. The final vector is Internet of Things and 5G. As you know, today we have close to 2 billion industrial and IoT connected devices. IoT security service market was close to 10 billion in 2021. and 90 million new 5G and IoT connected devices in 2026. So it's a massive market, and our solutions will need to cater to these requirements. What are the challenges for connected devices and the creators of them? More computing power and memory, lower power, an increase of sensors for data collection, easy connectivity, more security, and of course, faster time to market. How do we address these challenges? For computing, power and memory, obviously, more MIPS, more flops, graphics and AI accelerators, more embedded NVM, more flash. For power, ultra low power operating modes, efficient computing, system optimization. Sensors need to be of all hues and all colors and all specific requirements. Easy connectivity, more security will need more protocols, higher speeds, software security, and embedded hardware security. Faster time to market would mean ready-to-use hardware and software components, faster prototyping, easy transition to industrialization. So, key takeaways for us from this session. Innovation in semiconductors is essential for enabling key industry trends in the electronics industry today. ST's approach is as following. Long-term investments in the fundamental technologies needed to support this trend, targeting specific markets and applications that benefit from our technologies and drive the adoption, developing products and solutions that meet the needs of our customers, creating innovative, sustainable technologies in a very sustainable way. Thank you very much for your attention today.
Thank you, Ravi. That was a very nice talk, and I learned a lot and about different materials can be used across different markets. So, Ravi, I do have a question about this silicon carbide. It's very interesting to learn about this. So, I want to know what are the deterrents to adopt this in a wide scale?
I think, thank you, Vijay. So as of today, the market has quite vigorously adopted silicon carbide. The only problem or the minimal problem is more from a processing perspective, because unlike silicon, I mean, this is either on the solid state or in the gaseous state. So crystalline state is a little bit difficult, but I think the processing technology has caught up. I think there are ample providers of this solution. Among ST, a lot of the companies which deal in the power electronics segment, in the power electronics semiconductors, have over the last 20 years actually done a wonderful job of adopting this technology. The impact is minimal on cost. I see a question in the chat that is there a additional cost? Not
Right.
really. I think this is small and gets amortized from the benefits that we get, the tremendous benefits in reduction of the size, in the breakdown voltage going pretty high, in the miniaturization, in the weight reduction that we are able to give to the systems. So,
thanks, Ravi. I think that was the last question we had from the audience. And thank you, Ravi. Thanks for presenting at this industry forum and taking time. And yeah, it was very, very insightful. Thank you.
thanks a lot, Vijay.
Thank you. So next we have Ish, who's going. Let me first introduce Ish, who is a distinguished engineer at ARM in the Architecture and Technology Group. So with a background in computer science, Ish comes with a strong passion for computer architecture. Currently, Ish is driving the machine-readable specification strategy for ARM architecture. So Ish is going to talk about silicon catalyzing computing, communication, and cognitive convergence and sustainability. Thank you. Over to you, Ish.
Hi, this is Ish Dham. I'm an engineer at ARM, and I'd like to firstly take this opportunity to thank the VLSI Design Conference Committee for giving me an opportunity to come out here and talk. I want to take this opportunity to share something that I feel strongly about. Silicon clearly is at the core of everything we do, especially today, sitting here in this conference, we would certainly all agree with that. But is there opportunity to do this sustainably, right? What can the advancements in the silicon technology help in making our planet more sustainable, our not just our planet but our world more sustainable, including the people in here, right? That's what I want to kind of share here. I'm not quite an expert on this space, but I would like to share this as it's something that I feel strongly about. I come from ARM, so I'm using ARM examples, things that ARM is sharing out in the open. But this is not really meant to be a pitch of what ARM is doing. I'm using these examples because that's what is easier for me to do. I would like to, these are fairly generic examples, and I would like to take this as an opportunity for everyone to participate in this direction. So moving on, looking at how we could be approaching sustainability at ARM, we are looking at this from two key priorities, right? One, first of all, on the on the sustainability of the planet perspective in terms of decarbonizing compute, right? As the demand for digital technology grows, can they help in reducing environmental impact, not just of the compute, but perhaps the compute can help reduce help the carbon impact overall itself, right? And that is quite an imperative. I don't think that's a choice. That's just something that needs to kind of happen out. And this could be done in many ways. I mean, this is not a exhaustive list of how these could be accomplished. You could certainly be improving the performance of what we have. It is interesting that even though the compute usage has been increasing so drastically, the power requirement for data centers and so on has not increased by as much, right? And a lot of that has become possible because the performance, how much of loss goes into cooling and everything else has been managed, or the silicon has been made more efficient. Silicon technologies can play significant role in ensuring efficient distribution and utilization of energy. That's a significant factor that kind of comes in. One other interesting aspect that I'd like to actually touch upon a little more in this talk today is there are opportunities to impact where compute happens and how it happens, and this can have a significant impact on the carbon footprint of what we do as well. I think most significantly, use of compute technology can help enable alternatives, right? I mean, electric vehicles is a notable example, and there are plenty of other aspects that are getting enabled by new technology. A lot of it backed by compute and technology, automation and AI, right? So enabling alternatives is another significant aspect to be watchful for in some sense. So let's take a few examples, right? So here is something from a research that we had kind of participated in. If you look at, I mean, one of the things that cloud computing enables is it allows location of the computing servers anywhere in the world, right? And of course, this comes as a trade-off. If the server is located far off from you, there's an increased latency and so on. This is assessing, in an example, if you were to run a virtual machine on a server in Sydney versus moving it into Taiwan, it might be possible actually to cut the carbon consumption per VM from 6 grams to 4 grams, right? It might be simultaneously be possible to cut the cost by 15%, and you might be adding only 13 milliseconds of latency, right? So this is one of the aspects that that the new technologies enable, that by making these choices, you could be saving a lot of energy. But it's not just in terms of making those choices. The compute that is running and how it's running could make a significant amount of difference. So, for example, these are as per our calculations, the newest processors that we have been putting out focus towards data centers can significantly help reduce the carbon footprint by providing additional performance while taking much lesser energy. And it's not just the energy of the processors that matters here. A larger impact also comes from the requirements on cooling and so on, right? The less energy you consume in a on cooling a data center, the more you stand to gain as well. So there is a lot. And Neoverse is one example of specialized processing, but specialized processing by the use of GPUs, by special neural processing units or video encoding and decoding and so on have played a long way, and that is a significant way in which we are managing the end of Moore's law, so to say. The last bit in this context that is what my favorite is essentially how you can, by shifting what you do where, you could be making a significant impact. So if you were to look at smart cameras, connected video cameras on a cloud context, you can clearly see you have a choice on how much intelligence in terms of inferencing and so on you bake into the camera versus how much you do on the cloud, right? And if you took a naive approach of recording the video on the camera and sending it on the cloud and doing all the analytics there, you could have a cheaper camera, you could have a more energy efficient camera, but you would be shifting the compute onto the cloud side. But then you might be spending a lot of energy on the communication, sending a large stream of video across all the wire, right? But instead, if you were to shift a lot of the inferencing on the camera side, you might be able to get by sending only much reduced video across, and thereby reducing the energy requirement quite significantly. So these are simple sort of choices that we could be making, where we do compute, how we break up the compute between edge and cloud, and what we use for our computing element, right? And the computing element is not just a processor really, but it could be, these could be system choices. They can make a significant amount of difference. I said that in ARM, we were following two key strategies. The first one, decarbonizing compute. The second aspect that we are really trying to focus around is closing the digital divide, right? It's really important as compute starts to take the center stage that everyone is able to participate in that, right? Connecting everyone everywhere is essential for an equitable world, right? The increased digital divide is not going to be helping anyone, and this can all make good economic sense as well. So there's value for businesses to kind of invest in this direction. So again, I'd like to share a few simple examples in this context, but overall, looking at how we could be approaching it, you could be approaching it by improving connectivity, by making more, remote areas accessible over network and so on, improving affordability, making mobile more affordable, making other technologies more affordable, not just in terms of the machines, but also the data requirements and so on, the cost of any of that, right? So there is a significant way to impact that. We tend to think of everything as this connected world, but it is also important, especially as you want to bring inclusivity, to be able to share information even in off-grid contexts, right? There may be disruptive grid. We all know about that in our context. There may be remote areas that are not so connected. And another aspect that technology can enable is opening up services, right? Remote, whether it is health services or access to other amenities and everything else, how the technology can play a significant role in enabling that is quite key in many ways, in economic and inclusivity. So again, looking at a few quick examples, and one interesting bit is this Jungler box that can take any form of internet connectivity and enable a Wi-Fi hotspot very quickly with very little technical know-how anywhere, right? So you could be using 4G where it is available. You could use some other form of networking if it's available, or even satellite, right? And set up internet very quickly and be able to, and it's a light and portable thing that can be redeployed anywhere. And this has been utilized to enable connectivity for, in situations of, there's an earthquake, there may be refugees, there may be there may be a sudden disruption for some reason, some floods or some other pieces and so on. You can very quickly deploy the technologies and relocate them and make that possible. So that's something that can be, that's one key example. Here's another one, which is an Amplio talking book. It's meant to help information sharing in more educational contexts in low literacy environments. So it's a simple device that, as you can see, doesn't have any words on it. So everything is very visual. The content can be local language. It's audio content that people could be listening out. It can be powered by batteries available locally where even continuous power may not be available and so on. It doesn't require internet connectivity, so you can download stuff on it and share it. People can provide feedback through the whole system itself. And there's interesting choices being made here in terms of how to include just about everybody, women, children, the whole community in those contexts, and making it very purposeful and deployment. And I'm sure we can all relate to it quite strongly. Closer to home, here is an example of a wearable necklace. You can see the baby having this pendant. The pendant can record the immunology records on it, right? It's battery free, so you bring it on, you connect it, and you can download the additional data, and it is useful. And this has been deployed in Rajasthan, and it's a fairly it has some level of history now, and it is significantly useful in improving the participation in ways, right? So what I want to conclude on is saying that, clearly compute is becoming at the core of everything, right? But as that happens, it is really important that this happen. We pay attention to sustainability. It's not just what compute does, but what it can enable. And there is a lot of possibility here if you just think about how the pieces are. So what I want to encourage is everyone to consider that in some ways. Thank you.
Hey, thank you, Ish. This was a very heartwarming talk, I should say. And I should also say that I never knew this side of the ARM technology. So this is really, really heartfelt and heartwarming to know. And two dear topics to me, leaving a less carbon footprint and also reducing the digital divide, right? So I have one question. I know ARM is super successful in providing low power architectures, right? So are you exploring even beyond that to enable these kind of technologies, like a special ARM architectures for even, I should say, ultra low power applications?
Well, thanks so much, Vijay. Yeah, I mean, I think we certainly have a lot of processing going on into ultra low power, no power kind of context. There are plastic arm implementations that can be flexible, that can be running off power, that can be harvested from the environment, and so on. And as you know, we have done demonstrations ourselves, but really in terms of the implementations, those are really from our licensees and the ecosystem. But there are ARM implementations out there that work on really, really low power or almost no power as well. So yes.
Thanks, Ish. Thanks for this wonderful talk. I don't think we have any questions from the audience. So we'll go to the next speaker. Thank you, Ish.
Thank you very much.
So our next speaker is Tanay Karnik, who's a senior principal engineer and director of Heterogeneous Platforms Lab of Intel Labs. Previously, he was the director of Intel's University Research Office. He received his PhD in computer engineering from UIUC and joined Intel in 1995. His research interests are in the areas of heterogeneous integration, small form factor systems, 3D architectures, variation tolerance, power delivery, and architectures of novel devices. Today, Tanay is going to talk about trends and challenges in the most happening 2.5D and 3D integration for next generation chiplets. Over to you, Tanay.
Hello, and thank you for this opportunity to present at VLSID 2022. I am Tanay Karnik, presenting trends and challenges in 2.5D 3D integration for next generation chiplets. I have many slides, but let me try to do justice and cover all of them in 15 minutes. This is the legal information from Intel Corporation, so I'm not going through the details. The presentation is going to be roughly introduction, then motivation for 2.5D 3D integration, recent products, especially FPGA and Lakefield. That was actually done mainly designed in India side. And then advantages, challenges, where are we going? What is the future of 2.5D 3D? Before diving into details, just making sure people understand that blue are the called top chiplets that are on a gray base die, and they are connected in a 3D fashion. Top chiplets connected to base, and then base die connects on the C4 bumps or package side bumps to connect to organic package substrate. EMIB is on the right side, where it is showing that two base dies or two dies can connect to each other through an embedded silicon bridge, embedded multi-die interconnect bridge. And package traces are also there. They are shown in black. So essentially, 2.5D is many top dies on the base interposer. Interposer can be silicon, organic, or glass. There is also an optional patch on interposer that is inserted in the middle. I'm not showing that in here. And obviously there are high density packages, hybrid metal bonding techniques, etc. are coming up. So this is just to set the terminology right. Then I wanted to bring this to your attention that long time ago, okay, in 1965, Gordon Moore, who was the founder of Intel, actually said that it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. And clearly we will be able to build such component crammed equipment. So he was envisioning chiplets even like back then, long time ago. Revisiting the past. So what have we done in Intel Labs even before Intel products got into this 3D arena? We have shown that we can do processor. This is not an x86 processor. This is it's a high performance computing processor on top of embedded SRAM memory at the bottom, and we had 3D stacking of it. We had a regular processor with 3D stacked voltage regulator in the middle, sandwiched between the package and the die processor. And we have done some analytical studies and published about CPU DRAM combination in the 3D stacking. There have been challenges long time ago about manufacturing, assembly and testing, EDA, power delivery, hotspots. So 3D was not picking up. 3D actually exists since 1980 and TSV process exists since 1990s. So right now, these challenges, many challenges are overcome, but and continued technology scaling overcame the benefits of 3D at that time. And some of the challenges I'll bring up, so they have not gone. I'm going to present two motivations for 2.5D 3D integration. One is function dependent process selection. So if we plot performance, cost, leakage power, transistor design, target range, all of them with respect to each other, various parts fall into various different points on that chart. On the right side, we show that if we have a penta chart of density, leakage, high voltage requirement, passives requirement, and speed, and if we plot logic memory versus IO versus RF versus mixed signal, it becomes really obvious that not a same technology cannot satisfy all of these requirements. They have different function dependent requirements. What do we do about this problem? That's where the integration comes in. That's where chiplets come in. So you make chiplets that are optimized for a particular function, and then you integrate them in a package. That's what is 2.5 to 3D integration motivation, one of those. Second motivation is AI memory. If we look at the bytes per flop ratio and evolution of that, it's just going up and up and up. Okay, it's exploding. The graph is a bit dated, but we are seeing that 0.06 bytes per flop has become 25 terabytes per second requirement, which means we need a lot of memory feeding into the compute, and we have to bring memory closer to compute. HBM was a solution which is presented on the right side. HBM2E3 was proposed as an efficient way of low power solution for HBM bandwidth, and but it's still at 800 watts of power. There is 10x power efficiency gap. So as the performance and memory bandwidth requirement is getting higher, the energy efficiency gap is getting bigger. So we have to integrate more compute and memory together and feed the compute all the time. That is the second motivation for 2.5 to 3D integration. There are various techniques to do this, and many companies are working on it. Many foundries are working on it. Many OSATs are working on it. So if we plot interconnect density as a function of energy efficiency, it becomes obvious that standard packaging is bump pitch limited and it doesn't have that much bump density. Then hence Intel went to embedded bridge for FPGAs. Then for Lakefield, we went to Foveros technology. And then we are looking at future high density interconnects where bump pitches will be less than 10 microns, bump densities will be 10,000 per millimeter square, and energy per bit will go down to 0.05 picojoule per bit. Today we are talking about 0.2, 0.3 kind of picojoule per bit, and it is going really down for 2.5D integration. These are the recent products that Intel has demonstrated, and some of them are already offered. So in terms of heterogeneous integration, FPGAs were the first. Intel FPGAs integrated optical I/O over AIB. And there have been 2 IR Labs TeraPHY optical I/O chiplets connected to FPGA. This was published in 2019 and 2020. Lakefield was more in terms of form factor reduction. So it's a 3D stack of compute on top of a base die, active base die. And then there was also a package on package memory to make the form factor even less. We'll go through these 2 examples in a little bit more detail as we go forward. There is also an advantage of 3D stack of 2.5D is scalability. So if you connect things over EMIB or Foveros and you go on expanding the solution on the package, then you get really high compute capacity with memory attachment, HBM attachment, like what we are doing in Sapphire Rapids. We have announced this also. Ponte Vecchio has lots and lots of chips in 2.5D and 3D combinations. And the stack of Ponte Vecchio, which is really complicated, but it's working and it's on the right side bottom. So these are the proposed solutions from Intel in 2.5D 3D products, and better and better versions of these are happening. FPGAs, as I said, were the first. So in 2019, it was became apparent that family of FPGAs wanted to remain on the same node and with transceivers and chiplets to be updated. And that became the primary motivation of reducing platform cost. So FPGAs were maintained and then transceivers were separated. And FPGAs have always been most sensitive to device scaling, speed, density, memory bandwidth. All of that limits performance of the FPGA. And it was also shown that if transceiver is taken out of and made as a chiplet connected over EMIB, then we get better yield of the part. So we actually get we spend less money to make multiple chips than making a bigger chip of and including everything in one. So FPGAs in 2.5D fashion were connected over Intel EMIB. FPGA die in the middle, then there were EMIB embedded multi-die interconnect bridge on the sides, and then it was connecting to 24 channels, 28 gigabits per second PCI interfaces, and all of these were going to the transceivers. Now, what advantages we get is 14 nanometer 1 gigahertz FPGA stays constant, and transceiver roadmap now becomes independent of FPGA. So we can go on building better transceivers and connect to the same FPGA as long as we have the same interface that we are following. And that's the next slide. This slide shows that the enabling technology behind all of this is a standard interface. That's it. That is what is required. Intel made an advanced interface bus, AIB, completely open source. People can use AIB and its generators and follow the AIB spec, and you will get FPGA connectivity automatically. If you follow the same, then we can actually go on expanding different chiplets that connect to FPGAs over AIB. AIB 1.0 came into existence, then AIB 2.0 proposed, AIB 3D is happening. So the IO voltages are coming down, energy per bit is improving as we are going from AIB 1.0 to 2.0. And we have also made sure there is backward compatibility of AIB 2.0 to AIB 1.0. And all of this is available on the CHIPS Alliance, which Intel is part of, is a member. Second product that we have published and very about 2-3 years ago is Lakefield. The goals of the SoC were enable new class of compute devices in mobility form factor and compute at lowest thermal budgets and standby power. This was for a mobile computing part. What all this meant was 110 standard power. Standby power was a premium. We wanted to also show 50% graphics performance improvement, 40% core board area reduction, which was the form factor reduction that I was talking about, and 40% height reduction. So everything becomes a very small solution. How was this achieved? With Lakefield, a hybrid architecture with 3D-IC integration. So there are new hybrid IA cores, high performance cores, low power cores, GFX, media display, IPU, all of them in one die, connected over 3D die stack to all the off-chip IOs and sensor hub, and with on a base die. That became all together as a very small form factor solution for mobile parts, and Lakefield was offered, and it has been a good experience so far. In Lakefield, what did we achieve? So if we look at the Gen Y, if we see the Y, like mobile parts Y Gen 1 and Y Gen Y SKU, Lakefield is 0.4x of the original mobile Y solution, Core Y. Then package is very small, 12 by 12 only. Memory is small. PMIC is giving a, we are using PMIC instead of discrete VR in this solution. And then on the left side, we can show that the performance losses from TSVs is less than 1%. So 3D stacking is not really causing any loss in performance. It still works to the spec. So what are the advantages of 2.5D and 3D integration? We all know this, and it's a list that probably not a surprise. Lower portfolio costs, lower product costs, lower project costs. We can scale innovation and delivery capabilities. That means granular leverage of and process locked IP from internal and external sources. Granular leverage of manufacturing capabilities and capacity. 3D stacking benefits, obviously, XY area reduction, placing memory closer to logic. Also, we get a reduced time to solution. Reuse, reduce process availability, maturity, SKUs become faster. And with the scalability advantage of some of the base dies, we can even get 4x scalability over today. EMIB can connect bigger dies over EMIB, or a base die. If it is passive, it can be 4x scalability, meaning 4 times the biggest chip that we have produced, we can produce today with that much capacity in a package. But we are still facing similar challenges that existed in the past. Power delivery and thermals is in high performance, cost effective, high level solution is same as before. We have to manage the powers and have a better thermal solution. There is a tiling tax. There is an incremental area power performance overhead because of die-to-die interface. There's incremental package assembly test cost, duration, and tolerance requirements impacting throughput time, inventory management. Sometimes it is impractical to co-package multiple hot die and die that need a large amount of external PCB connectivity. There's also margin stacking, inventory carrying costs when using external die. There are no optimal cases in which a monolithic alternative is feasible. Die design for a 3D stack is difficult to use sometimes because there is no unbonding. And then enabling IP software tools, flows, methods, all of that is remaining. These are bigger challenges that we have to solve. Hardware is not the only puzzle here. And we need fully specified interface standards. And that's my next slide to show what is interface standardization. We need mechanical standardization, we need thermal standardization, we need electrical standardization, and we need functional standardization. All of those have to happen to support a generational capability, meaning generation over generation, we can go on producing new solutions with the same interfaces. This can all be enabled by off-the-shelf tool flows methods that can be offered by either design companies or EDA companies. And we need hardware software building blocks. And all of this, when it comes together, it supports the industry scale systematic reuse. We have to talk about software because everything is software driven these days. So we are on one side, we have board level integration. On the other side, we have on die integration. All of that is coming together as a package level integration today in chiplet world. So ideally, we need a uniform software. Like software should look the same for any kind of integration. So ideally, IP and associated application software should be agnostic to scaling and physical integration approach. And this will enable right sizing functionality for a wide variety of target deployment environments with high reuse of IP, system, and software investments. So system is not just hardware, system is also software. Don't forget that. I want to make sure that you get that message. So finally, to conclude my talk, it's a very short talk and thank you for listening. 2.5D and 3D has become mainstream. All products are 2.5D or 3D. Many old challenges are mitigated, but some still remain. 3D, this integration provides reduced overall product cost with higher energy efficiency. And two more pictures to show where we are going. One is Foveros Omni, where we have a ability for a top die to go directly to the package without going through the base die. And then Foveros Direct, which is Intel's way of hybrid bonding. So Foveros Direct is going to be less than 10 micron pitches, no micro bumps, copper to copper attach, two different dies. And then once you get such a high density, then you have 10,000s of connections per millimeter square. And you can have really, really serious 3D stacked memories or compute or accelerators or whatever you can think of. With that, I would like to conclude. Thank you.
Hey, thank you, Tanay. That was very, very insightful and the most happening technology, and Intel spearheading the leadership, I would say, in that both 2.5D and 3D, while other companies are still trying to catch up, right? So I have one question for you. Even in yesterday's talk, I heard about the simulation models or the abstractions that you need to build around this stacked dies, right? So and you also kind of briefly touched upon this. So what are the challenges in terms of doing a verification of this type of an SoC?
We also face exactly the same challenge as you are saying. There are tools coming up, but not enough. They are not easy to use yet, and they don't scale for really large dies. But yes, you have to model. Let's say two dies are talking to each other. You have to model a transceiver to a microphone to a trace to another microphone to a receiver, and all of that has to be correct. And yeah, these kind of extraction tools in the physical domain for the channel and communicating across two dies has also close timing has become a challenge for us, and we do take advantage of the receiver side DLLs, like we do delay locking and phase matching on the receiver side, and we do transmitter trimming on the other side, but still we are looking for better and better tools. Yeah, EDA tools are not there yet to
Right.
use the really large silicons and connecting them together. You are absolutely right.
Thanks, Tanay. And we do have a couple of questions from the audience. I'll just read them to you. As D2D bandwidth is limited more due to micro bump pitch and we getting into more die disaggregation, is protocol level enhancement considered to aid the cause?
Yes, so we are in Intel, we are also looking at protocols. So recently announced CXL protocol. CXL, Compute Express Link. And yeah, we are looking at CXL to scale for die-to-die interconnect as well as die-to-off-package interconnect. And we are trying to proliferate CXL as a memory, cache, and I/O, 3 different ways. And but this question is valid. Yeah, protocols also have to talk to each other. Something like PCIe has to happen in this world, and all companies admit that standardization is important. There has to be standard protocol, but all companies are proposing their own standards. That is not a standard. You have to come together to one standard. And yeah, things are happening. You will be seeing some announcements very soon. How we connect over CF.
Thank you. There's a last question for you. How is EMIB better than regular interposer die?
Okay. So it's not an easy question to answer. So EMIB is a very small piece of silicon. So if you're talking about connectivity only between 2 dies, then EMIB becomes more cost effective because it's a smaller piece of silicon. And then the top dies can be of large size connecting over EMIB. That's given. The problem with EMIB is that it's an aerial connection, meaning it's not an aerial connection, which means you have to drop your IOs at the side of one die and receiver should be on the side of the other die. When you have an interposer die, you can connect any point of the die to any point of the die on the other die. So actually interposer die gives you better connectivity between the 2 dies, but then you have to pay for the silicon cost of the larger base die. So it's a trade-off between silicon size of the base die, if we call EMIB die as a base die, is the silicon size versus how many connections can flow from one die to another. That's the trade-off here.
Thanks, Dane. And one last question from me. So when you are actually splitting this SoC into 2 different dies, right? And when you stack them, are they roughly similar size or not necessary?
No, there is no necessity for top dies and base die. They have no size relationship. In fact, there are proposals of making base dies smaller than top dies. So various different things are happening. I mean, this field is just exploding. Many people are working on this field right now, and we need. Okay, one more thing I should say is system level exploration. Okay, something as a challenge. So if somebody gives you like a workload, a set of workloads, and okay, come up with a system for these workloads, we are looking for tools that can actually give us an advice as to how many chiplets do we need, what each chiplet should have, what kind of IPs, what kind of interfaces, and how all of this should come together. So system level tools are also something missing today.
Thanks, Tanay. And yes, that concludes our industry forum sessions. And we had lots of good speakers. And thanks to all the speakers for excellent talks.